Perfect. Nice. So the first lecture is going. This lecture is going to be about interpretable machine learning, and basically it's about interpretability. We're going to speak about many topics, mainly interpretability in general, what it is, and then we will speak a little bit about one simple algorithm for interpretability, and then we will speak about how to do interpretability for computer vision. So during today's lecture, we will see interpretability for basic models, interpretability for more complicated models, and then we will see interpretability for computer vision and interpretability for text models. So it's as I said, it's quite simple, so it's very basic, don't worry. So first, we would like to get a little bit of an introduction into what is interpretability. And I think before I go into the lecture, I want to give you like a resource that I don't want to remember about, to forget about. Let me just... This will be like a very, very important resource for you guys to. Share the screen again. This book, extremely highly recommended reading. It's a very simple book. It's free, and it covers exactly everything we will see during this lecture, besides the final computer vision interpretability part. But everything else, you will find it here. The concepts that we will speak about, interpretability, what it is, the importance of interpretability, the taxonomy of interpretability, the scopes and different levels of interpretability. And then, of course, we will speak about the interpretable models, how they are, the models that are not interpretable, and how we can basically interpret them. And then it will speak about LIME. After this part, the lecture becomes a little bit more independent from this book, but this book is extremely important if anybody of you wants to go into this field of machine learning, interpretable machine learning, then this is like an absolute must, right? So definitely do take a look at it. I'll send you this reference. I'll put it on Moodle and I will send you this on Telegram. Okay, let me just put it also on Moodle. So as I said, it's actually a very, very beautiful book. I'm not a book reader personally, but this one is super easy to read. And I think it's quite nice to look at. Nice. Let's continue with the lecture there. Yep. So before we go into like the algorithms and the difficult parts
Imad,
of yes.
you don't see your screen.
Oh, okay. Now?
Yes, thank you.
Thank you so much for telling me. So before we go into more depth about what are the algorithms used to perform for like interpretability for computer vision, interpretability for text models and natural language processing, let's first speak about interpretability, what it is, the scopes of interpretability, the different levels that we can have in interpretability, and then of course we speak a little bit about simple basic models and how we can interpret them. So this is an image. I'm not sure if you guys can see this very well. Let me just zoom in. Can anybody tell me what is this animal?
Horse.
Horse, right? So no human being would tell me that this is a camel, right?
Yeah.
Yes, but sadly, a machine learning model, when it looks at this, it will tell you that this animal is an Arabian camel, right? With a very high certainty compared to basically this wrong answer. Can somebody guess why would a machine learning model confuse a very easy and simple, clear horse?
The environment.
Because of the environment, exactly. So the model that we used here is ResNet 50, which is definitely a very well-trained model. So it's not like trained on a small data set and it has a lots of bias and stuff. No, it's trained on a very gigantic data set and it understands very well what a horse is and what a camel is. But since there was a change in the background, now this horse is in a place where the data set, the training data set did not predict a horse would be in. The model is now predicting it as an Arabian camel just because of the background. But how can you make sure that the model is, is predicting correctly based on the animal itself? And when the model is just acting up weirdly just because of the background, right? So we do need this layer of interpretability that tells us whether the model is, focusing on the most important parts of the image, or if the model is making its decisions only based on like useless background information. And this is where interpretability techniques come in, right? So here in the interpretability techniques, we can see that the model is looking at the architecture of this thing. It's looking at the sand. It's looking at this, what is it called? Palm trees. It's looking at the background. It does look at the animal a little bit, but it's not the main focus of the model, right? So the model is very, very noisy, or the model is taking into consideration many things that are not part of the image. So this is one of the reasons why we need interpretability. Can anybody tell me like other reasons why we might need interpretability in machine learning, right? So for example, take the example of a bank system, right? So a bank system that tells people whether they have the right to get a loan and buy a house or not. So this is a machine learning model that can decide the rest of your life and your children's life, right? Whether you're going to be rich or not. What do you think, interpretability's importance is in such models?
I think it's very important because it makes a huge decision for a person, and if it says no, we have to know like why is it no, why is this person bad, and what he can improve.
Exactly. So first thing is it tells the people why they were rejected and how they can improve. So that's reason number one. But it also tells us whether the model is racist or not, right? So for example, you take the example of a black person going into like the bank trying to get a loan, but the loan rejects him, or the machine learning model rejects him just because he is black, right? So that's not something that he's going to be able to change. That's something that's going to tell us we need to change our model, right? So that's the main reason, right? So first reason is to give humans the ability to make changes in their lives. So it's not something that is completely, what is it called? Random. So you don't just go randomly and that just tells you no, and life is super random. It gives some reasoning to life, right? Especially since it's being used in very, very important places. And the second part is it's very important to make sure that these models are not, affecting people's lives in a bad way, right? So they're not continuing some racist ideologies, or like pushing the gap further between the multiple races, right? So that's another example of why, what is it called? Interpretability is very, very important. So in terms of fairness, in terms of like making sure that there is like some causality understanding, the trust for the like people's trust to the system, right? So for example, I don't know, like you are building in Twitter, their recommender system now just recommends you a lot of bad things for you, or like for your child. Do you trust that model? Yes or no, right? So how can you trust it? You need to understand why it is, showing your kids things that you don't deem appropriate to their age. And once it tells you that, you can start making some changes. So for example, I don't know, start liking different pages, start following specific people that show age-appropriate content to those kids. So this is why we need interpretability. It just helps us understand the model better and helps us change the model's behavior in a more predictable way. So these are some of the reasons that we need interpretability, right? So here we have a couple of them mentioned. So the first one is satisfying the human curiosity, just why, right? Improving recommendations. So as we said, so instead of just showing you anything that the model just says, you can have this idea of understanding why the model is showing you what it's showing you and how you can influence it just by following other people, putting a lot more likes on the content that you like, or for example, if you interact with some hate speech, even though you don't like that hate speech, the fact that you interacted with it makes the model think that you're interested in such content and keeps on showing you again and again. So probably the best way to not get that hate speech is to not interact with it completely and ignore it. And hence the recommender system is just not going to give it to you. For safety measures, as we said, for different systems, there are some measures, like some critical systems that we need to make sure that we understand how they work. Detecting biases against, of course, people of color or, minorities. And the most important thing, which is debugging and auditing your model, making sure that it's still working and it's not making stupid errors, right? So it's not just looking at the background and telling you, oh, let's just do that and you're all good, right? So for example, there was a case where they built a machine learning model to detect skin cancer. And apparently in the data set, the people who were like the people who had skin cancer, the doctor usually puts a what is it called? A measuring tape in front of the skin cancer, just so that he gives like reference for the size of the skin cancer. Whereas the people who don't have the skin cancer, the doctor just usually takes a picture directly and doesn't give reference with a ruler. So the model in the end was not training on detecting the skin cancer. It was just a simple ruler detecting model. And you would never be able to identify that if you don't debug and audit your model using some interpretability technique that tell you the model is completely ignoring cancer. It's only looking at the ruler part. So now let's go to the scopes of, of what is it called? Of interpretability, right? There are 5 levels of interpretability. The first level is very basic, algorithm transparency. This level is definitely the most controversial because it's not something that we can always have, especially in, the type of economy that we're living in. And basically what it means is, how does the algorithm create the model? Now, this question is very important, right? So for example, if you go to linear regression, this is something that we all know how to train a linear regression. But if you go to Pepsi or you go to Twitter and you go to, I don't know, Netflix and how they do the recommender systems, you really are not going to be able to know for a fact all the details needed to recreate their algorithm, right? So they're not going to give you all the information about their algorithm. So algorithm transparency is something that is definitely very hard to achieve. What we could achieve is just a lighter version of it. So it just tells you that maybe it's a linear model, or it's a non-linear model, or maybe it's a certain combination of techniques or stuff like that. But definitely we're not going to be able to have access to all the algorithm itself that was used to train the model, right? So they're not going to just open source all of the machine learning code in the world. So the algorithm transparency scope, which is the first scope, is a very difficult level to achieve and definitely not something that we can wish for. The second level is the global holistic model interpretability. So it's a lot of words, but the goal is to ask a question. The question is, how does the trained model make its predictions? So say, for example, you have linear regression, and we will take the example of exactly linear regression in the next slide. But the question here that we're trying to ask is, how does a trained model make predictions? Does it multiply, I don't know, the inputs with some weights and then do the summation, and then there you have it? Or is it a computer vision model? So it takes the image and then do some pre-processing and then, sorry, Siri is activated, sorry. Nice. So is it a computer vision model, as we said, and it just takes the image, pre-process it, send it through the CNNs, and then send it through a fully connected neural network, and then gives you the output, or what's happening, right? So how do we go from inputs to outputs once the model is fully trained? The third level is global model interpretability on a modular level. This tries to ask the question of how do parts of the model affect the predictions. So for a simple model, for example, like linear regression, we know that if a coefficient is very high, that means this feature is very important, and we could and it's being used mainly to make the predictions, right? So it's influencing the predictions very highly. Whereas if this, what is it called? If this coefficient is not very high, that means it's not influencing the predictions that much. So we do understand the relationship between the different parts of the model, and how they affect the prediction. But if we speak in terms of, I don't know, like a gigantic neural network model, we're not going to be able to say that this neuron affects the predictions in this way, right? So it makes no sense to ask such question for such large models, and mainly because our understanding does not go that deep, right? So one very important concept lately is coming, that we don't really want interpretability to be like a complete obligation for different models, because you could easily write the list of functions that correlate or that link basically that neuron to the output, and then you would give the human being a, I don't know, 3,000 page just of maths related to that neuron and how it affects the predictions. But those 3,000 pages, although yes, it is like interpretability of the model, but it's not something that the human being can understand. So it's definitely not useful. So we have to take this third step into the context of, it must be something that the human being can understand, right? So
Excuse
how
me.
do different, yes?
Can I just, I'm not sure about the last point, the global model interpretability on a modular level. Are we talking modular as with like any part of the model should be understandable, should be interpretable? That's what it means?
Yes, so basically the weights of the neural network, how can we understand them, right? So for example, if it was just a linear model, it's very simple to understand. As I said, a high value for that feature, or high value for that coefficient, means the corresponding feature is very important. But for a neural network, a high value for a certain weight in a middle neuron makes no sense to us, right? What if we set it to 0? Does the model completely change? We have no idea.
Okay. So I just wanted to understand how detailed the interpretability is expected. So
exactly. So we go back again to the level of human understandability, right? So if we go down to the lowest level of understanding, humans are definitely not going to be able to understand anything, right? Because it's just a lot of math, and it would take a long time for a human being to wrap their head around just one weight in that neural network. But if we take like a step back, and we don't consider the whole neural network as just a bunch of weights, but think of it as, architectures. So for example, if we speak about the autoencoder architecture, human beings do understand, like, for example, the encoder is responsible for this, that, and that, and it affects the predictions in this way and that way. And the decoder is responsible for this, that, and that, and it takes the vector representation and then spits out the image again. So we understand a little bit how in globally they work, but we don't know like the deeper details, right? So if we go down to the lowest level possible, we're not going to be able to understand it. So it's a bit of a trade-off between what a human being can understand and what, of course, the absolute implementation of this scope would be, right? So again, the third level would be, how do different parts of the model affect the predictions? So it could be related a little bit to the second level, which is how does a trained model make its predictions? So definitely understanding how can we make the predictions in the first place would help us understand how the different parts affect the predictions, but that's not like an always strict rule, right? So as we said, in the neural networks, we understand that it's just a multiplication and addition with the different weights, and then it's just some non-linearity, but we don't understand how they affect the model. So they're definitely extremely related, but they're not like equivalent, right? So the first scope is to understand how the algorithm trains the model, how is the training function, basically. The second step would be to understand the predict function, right? So we have the predict function, and we would like to understand how does it work. The third scope is to understand how the different parts of the function, how the different parts of the model affect the predictions. And the last two scopes are simplest, right? These are the scopes that are easily expected from any company out there, whereas the first three are definitely a little bit more tricky. So the last two scopes are local interpretability for a single prediction, meaning why did the model make a certain prediction for an instance? So for example, you go to a bank, you ask for a loan, they tell you, no, we cannot give you, and here's the reason. This is easy, right? This has no, when they give you this information, they're not going to tell you anything about the model, right? So they're not going to tell you we're using a linear model, or we're using neural network, or we're using this architecture, or the weight of this neuron and this this connection between these two neurons is 3.77. They're not going to tell you all of this information. All they will tell you is increase your income and come back again. So this is a very simple level that we can ask from any company out there that is doing AI, which is the local interpretability for a single prediction. And this is something that you can easily verify. For example, on Facebook, you could double click on whatever image you're seeing, and it will tell you, why am I seeing this? And gives you some reasons to why are you looking at that specific image in Facebook. And then, of course, the fifth scope is the local interpretability, but not for a single prediction, but for a group of predictions. This is very much related, but instead of why did it make a certain prediction for a certain instance, we're trying to ask it, why did the model make specific predictions for a group of instances? So for example, if every time a black guy comes to your bank and asks for a loan, you reject them, you should be able to ask the question, why did the model make that, right? So was it because they were black? Was it because for some reason it was just like randomly that the black people that came today were not, rich enough to ask for a specific loan? Or maybe because of the type of loan that they were asking for, maybe it was too high for their income or something like that. So you would want to understand globally or in a group manner, why did the model make its predictions for these groups of instances, right? So whether be it race groups, whether be it gender, for example, we have the example of Apple Pay not giving women money in the same way that it would give a man, right? So the only thing that's different between the two accounts is that this one is male, this one is female, and the interest that it's proposing for women is much higher than the interest that it's proposing for men. And when they did the interpretability for it, it just turned out to be, a bit sexist, right? So, and that's from Apple. So this is something that is very, very that's touching, you know, everybody. So it's not like something that is you know, specific only to models that are trained on smaller data set or something like that. So even models that are trained on millions and millions of images are extremely biased towards the data they were trained on. So now let's go to like specific examples of very easy to interpret models, which are, you know, logistic regression. And if we could go through the scopes of interpretability very quickly. How does the algorithm create the model? So how do you train logistic regression, right? So you have some couple of coefficients and you keep on adjusting them until you reach like the perfect or the lowest, what is it called? MSE, right? Mean squared error possible. How does the trained model make its predictions? Also very easy. It just takes the input, multiplies them with their coefficients, and then do the summation. There you go. That's logistic regression. The second question is, how do parts of the model affect the predictions, right? So we have the higher the what is it called? The higher the coefficient is, so if we have a coefficient is set to 5 and another coefficient is set to 3, we can clearly understand that this coefficient is correlated or related to a feature that is very important compared to the other one. Local interpretability for a single prediction, we can easily just tell him, for example, if you increase a little bit if you increase a little bit the income, you would go to the other class of yes, you can get the loan, right? So just by changing a little bit the inputs, we see what happens to the output and we tell him what is the smallest change you can make to get towards the place that you want to get to. And then, of course, the final part is the local interpretability for a group of predictions. And this one is a bit more complicated, so it would need a little bit of, you know, an algorithm to handle this one. The second very simple or very basic algorithm that we will take a look at is decision trees. So again, we will go through them very quickly. So algorithm transparency, the first scope, very basic algorithm. How does the algorithm create the model? So at every step, we try to find, you know, the feature that gives us the most information gain based on entropy. And we keep on splitting and splitting and splitting and splitting until we have the best information gain, or the best, what is it called? The best entropy in the nodes. So this is the algorithm transparency. Where when it comes to the second level, how does a trained model make its predictions? It's very simple. You take the input, a couple of if statements, and then you give the prediction at the end. The third level, global model interpretability on a modular level. So how do parts of the model affect the predictions? Very easy. Again, we just give them this if statement is executed if you satisfy these three different if statements, and it would lead to a 30% probability of going to yes and a 70% probability of going to no. So we can understand how the different parts of this decision tree affect basically the prediction. Local interpretability for a single prediction, again, very simple. You just give them the if statements that led to that prediction. And if we want them to change it, they can just, I will ask you guys how we can change it later on. And the final level, which is local interpretability for a group of predictions, again, this is something that would require a algorithm to do it, but it's also a very simple thing to do. So it's definitely very easy to do. I have a couple of questions for you. How to explain a prediction on a certain sample? I already answered this, but just want to confirm.
Can you please repeat the question?
It's written here. How to explain a prediction on a certain example for the case of decision trees.
Can I give it a try?
Yes. So you have
Okay.
decision tree. How can you explain why did we refuse you?
Okay, so according to certain input, certain feature of the input, you are being placed in this first subgroup that corresponds to, for example, a subtree. For example, because of your income, you have been put in this subtree, and then because of your number of children, you've been put in the subtree, and in the subtree, we have seen that 90% of people do not pay their loan back, so you are 90% likely not to pay, so we're refused.
Perfect, exactly that. So you just give them the traversed part of the tree that they went through, basically because of their input, right? So you just tell them you have income that is lower than 100,000. You have more than 6 kids. You did not do a master's degree, so your education is not to the fullest. You did something like that. So you just give him the parts of the tree that are related to his prediction. How to change the class of a prediction? Or in simpler terms, what is the simplest way that you could change the class of a prediction?
May I?
Yeah.
I think it's to choose probably the feature that makes the first split. I mean, it depends. It's not definitely, but we can just choose the feature that decides which I'd say that makes the most influence. For example, here we can say that if for example the annual salary divides the clients into, for example, a subtree with 80% accepted and another subtree with only 20% accepted, then increasing the salary is the factor that will make it more likely for the client to be accepted in future.
But the question,
attempt.
right? So let's do it like this. So the first node here, for example, as you said, is salary. And our if statement is highly unrealistic. So for example, it says if salary above $1 million, then we treat them separately. If salary under $1 million, we treat them here. So we can't just tell them to get a salary above $1 million, right? But
isn't that a bug in the model in the first place? That says a lot about the model then.
no, but that's a model that could be trained, right? So we have 2 categories of clients. We're not going to ask them to just go to that different category. What if there is something already here? So what you're asking is to start from the start of the tree?
Not necessarily. What I'm asking is about to choose which, how can I say this?
So let's
Which
say he is
node
here.
makes most difference, in the sense that, for example, if we have before that node, we have, for example, a sample of 8,000, and then after this node we have a more balanced, like divided by 2, for example, sample of 400K and another sample of 400K. This means that this is more deterministic. For example, in the example you just gave, this will give us a very unbalanced, very unbalanced 2 samples or 2 subtrees. So I think we can choose the one that gives the most balanced subtree.
That could be the case, right? You start at the top and then you go down, right? Or you could start from down and you go up, right? So you already know that if they change from this to this, then they will have to traverse another tree in here and it will do a lot more calculations, right? But they are already here. And if this last if statement is an if statement that is logical, then one side is yes, the other side is no. So what we could do is just tell them to change the last if statement. They're already satisfying all of these criteria for a yes. It's just the last criteria that is not satisfied. We could tell them to try and change this. If that's the case, we could tell them to try and go up here and change this and all of its nodes, right? So we're not going to just tell them to change this part and keep, the place that goes to no, but we're going to tell them to change this part and make sure that this condition is also satisfied. And the higher we go up, the more conditions we put on him, right? Make sense?
And let's hope we don't ask them to lose one of their kids or something.
Oh, well, we should. Exactly. So yeah, so definitely there are some cases where it's dependent on the situation, right? So as you said, losing some kids, or I don't know, if they are married or not married, we're not going to tell them to just get married right away. but it's very very reasonable to say that married people get better deals for loans because they are, already in a committed relationship. They're not going to run away with the money, right? They're trying to make this work, and they're probably going to stay there for a longer term. So when they apply for a 30-year commitment, you can still trust them, right? But you're not going to tell him to just go and, I don't know, get married and have one kid immediately in order to get the loan. So that's not very realistic. So it depends on exactly the decision tree, but in general terms, you could try to go either from down and go up, or you could try to go up and give him the perfect trajectory that that would give the lowest, the best probability of getting the success, right? So two ways, either top down or bottom up. It's up to you. Now, we're not going to ask you to implement an algorithm for this one, but it's just to see if you guys can actually, think about it and propose something. And that's the point of it. The final question is how to measure the importance of different features. So remember, in the in the scopes of interpretability, we said level 3, global model interpretability on a modular level. It tells us how do parts of the model affect the predictions. This is another way to look at it, how to measure the importance of features for a decision tree. So for example, if a feature is used at the start of the decision tree, does that mean it's a very important feature? Or if a feature is used at the very, very lowest lowest level of the decision tree, does that mean it's more important? So which one is more important? Or more important?
Excuse me, can you please repeat the question?
How do you understand which feature is more important in a decision tree, right?
If it splits in half the data set, because if it splits into unequal subgroups, then it's not really helpful for us to make a decision.
And how do you find that best feature? How can you get it, right? So it's the feature that gives you the highest information gain. And when do we use that feature with the highest information gain?
Usually before splitting, right?
Yeah, in
To
the
determine.
exactly, in the first level. So the first time we come in, we have all the features. We try and use all the features to split. And then the feature that gives us the best information gain, we use that as the first feature to do the split. And then at the second level, we do exactly the same thing. And then at the third level, we do exactly the same thing. So at every level, we're trying to calculate the information gain based on the features that we get. And of course, we use that as the feature to split on at that moment. Meaning, if we want to interpret the importance of the features after the model is being trained, it's a very simple process. You just take the order of the features. So the first feature that is being used to split is the most important, and then we go down and down and down and down. Of course, in the case of numeric features, they can reappear in different parts of the model and at different levels. That's completely normal. So that's a specific case that you should, take into consideration when you're building such an algorithm, but just something to keep in mind when you're developing it. So as you can see, interpretability has no correct or wrong answers, right? So you can always imagine any type of answer that you want, and it's probably correct and wrong at the same time, right? So it's correct for some cases, it's horrible for other cases, and that's life. So in interpretability, there's no right answers.
Excuse me. What I mean, I've seen also the term fairness in machine learning, but I'm not sure how it's I think it's quite related to interpretability, but I'm not really sure.
You mean fairness, right?
Fairness, yeah, fairness.
Yeah, fairness is, do you speak Arabic?
Yeah, yes, of course.
Yeah, it's al-adl, adil. Right, so fairness is a concept of you're a judge and you're trying to make a decision on somebody, does that decision, is that a fair decision? So is that a decision that is based on objective facts, or is it based on subjective biases that you have? So for example, you're a white judge, and every time you see a black guy, you just send him to jail for life. And every time you see a white guy, you just give him 2 years in prison. That's not a fair judge. That, if that was in AI, that would not be a fair AI, of course, right? So AI is now, of course, reaching in different places. And now we have even like Tesla cars, they don't predict, for example, black people as pedestrians. So they're more likely to
Interesting.
yeah, because sadly they just trained it on white people, right? So because they had a lot of white people there, and not even white women, so it's only white men that are detected as pedestrians, like very perfectly. Everything else gets hit by the car. So of course, not always, but it does have this very, very steep degradation of the results. And this is the concept of fairness, right? So it should be a fair model that does not push forward the biases that we already have in life. And that's not something that we can fix using interpretability, but it is something that we can detect using interpretability. So interpretability is not going to change the world, right? So interpretability is not going to, I don't know, make us change immediately and become a less racist race, right? Human beings. But it is going to help us detect these biases, detect these unfair traits of the model. Does that
Understand that? Yes, yes, understand. Thank you.
And if you want, let me send you this link. Yep. So here, if you go to this link and the what is it called? Importance of interpretability link, he does go deeper into the concepts of fairness, privacy, causality, and trust, and it's a little bit down, like around the end. So you could just read a little bit more into that, right? So as I said, this is a very simple book to read. It's not one of those ugly books that just complicate things. This is a very basic book that gives very beautiful examples. Definitely very recommended, highly recommended reading. So we have seen the different, we have seen what is interpretability, the importance of interpretability in our world, in our lives. We have seen the different scopes of interpretability. The first one being algorithm transparency. The second one being global holistic model interpretability. The third, global model interpretability on a modular level. Local interpretability for a single prediction, and then finally, local interpretability for a group of predictions. Afterwards, we have seen a couple of easily interpretable models, which are logistic regression or linear regression, and decision trees. Now let's go to the world where things are not as easy, right? So in a situation where we don't have the algorithm transparency, or we don't have the global holistic model interpretability and the global model interpretability on a modular level, we only have the two final scopes of interpretability, which is just basically local interpretability for a single prediction, and then you can make some changes to that to give you local interpretability for a group of predictions. And this gets us to the local surrogate model. So LIME is a technique that is used to interpret black box models. So black box models are just models that you have no idea how they were built or how they are operating inside, right? So you don't have access to their code, you don't have access to anything in there, you have no idea if it's a neural network or just a logistic regression. You have no idea if it's a supervised, trained on a supervised manner or unsupervised manner. You have no idea what's happening, right? All you know is that it's a black box and you're trying to interpret its decision. So the first example that we're going to study it for is tabular data, as we said, and then we will take a generalization to text and images. And after that, we will take a look at GradCam, which is the final part of the lecture, basically the example for convolutional neural networks. So I think for now, what we could do is take a 5-minute break. And how much time do we still have in the lecture?
40 minutes.
30 minutes, right? 40 minutes or 35.
40.
Nice. So let's come back at 10:10. Have a drink, stretch a little bit, and come back. I hope you guys are back for now. All good? Okay, nobody's back. Some of you are back. Okay, that's
Yeah,
nice.
we're here. We're here.
We are
Nice. So now let's talk about LIME. So LIME is a very simple technique. It's called local interpretable model agnostic explanations. And if you would like to study it a little bit deeper, here is the link, and I'll send it again also on Telegram. This is a very important also reading because LIME is going to be the most important part of the midterm for the interpretability part, right? So we're now going to be asking you what are the different, I don't know, why is, I don't know, just like the most important questions will be about LIME, that's for sure. So LIME is, as I said, a very simple technique, right? So instead of interpreting this global nonlinear neural network based probably a model that has a very, very complex decision boundary, right? So you see this decision boundary? This is a very nonlinear decision boundary. This is the thing that splits yes, you get a loan, and no, you don't get a loan. But as you can see, it's very complicated, and we're not going to be able to describe all of these different corners in a text format that a human being can understand. So instead of doing that, what we will be doing is locally, so here, sorry, let me just come here. So here, as you can see, this is a very complex model in general, but if you zoom in, and if you zoom in even more, right? Imagine you're zooming in even more in that region, in this specific region, the model is no longer complex, right? The more you zoom in, the more locally you are working, the less complicated the model gets. We're no longer speaking about a complex decision boundary. Here, this can easily be estimated using a, what is it called? Sorry, let me try to give you some colors. Yep, so, nope. So this can be easily estimated using a linear regression, right? Only this small part. This is something that a logistic regression would train on very simply. And that's the exact purpose of LIME. So LIME, what it does, it just zooms in, extremely zooms in towards the place of the prediction. This is the place where we want to make the prediction. This is the example of the human being that we're trying to understand. And what we do is we zoom in into that sample and we just look around it. Around it, very much zoomed in, we see that it's much easier to make predictions or much easier to train a linear model on this region than it is to train a linear model on a gigantic part of the neural network. Let me just go back. So we're not going to be able to train a linear model on all of this, but we are going to be able to train a linear model on this. So what we do, as we said, we zoom in, we look at this region, and we just create some fake samples, right? So if our data set does not contain enough parts around enough points around these two, around this region, what we could do, we can generate some random points, right? We already know the class for all of these, right? Because we have the model, we can just make the prediction for any random numbers that we want. So what we do is we generate numbers around this region. We create the class for all of these different numbers or for all of these different new samples. And we simply train a linear regression or a logistic regression. The thing about linear regression or logistic regression is that they are very simple models, right? So these are models that you can easily interpret. So what we're doing here is instead of interpreting like the third level of local interpretability level, instead of interpreting the global nonlinear complex model, we just train a very small linear model locally in here and interpret that. We interpret that simple linear model that is trained extremely locally. So let's talk about it again. So the first thing you have to do is to select an instance of interest. So this is the person that comes to your bank and asks for the loan. He has some information, some input data. He is, I don't know, like he has $100,000 in his bank account already, and he gets a salary of $60,000 a year. And he has 3 kids and he's already married. So we already know where he is located. What do we do after that? This is the point here, right? So we select it. What we do is we create a random data set, or as we can see in here, perturb your data set and get a black box predictions for these new points. So we basically do just take some random points around the data set and we just make the predictions for them. The points that are on this blue part will be predicted class blue. The points that are on the gray part will be predicted as gray, right? So we have 2 classes. Third step, we have to weight each new sample according to their proximity to the interest point. So for example, the points that are very close to this yellow part will have a higher weight for their loss function, right? So as you know, there is something called as sample weights when you're calculating the loss, for example, for any model. Take it a model like linear regression, logistic regression, or even neural networks. So a weight, it just gets multiplied by the loss for that sample. We add that, we create this weight for each new sample. For example, here, the closer you are, the higher the size of the point. This is just a reflection of basically the weight. And the ones that are very far from the point are not very important, but we still keep them just for the sake of making sure that we are not blindsiding our model. What we do then, we train a weighted interpretable model on the dataset with these variations. So we only train them on this dataset that we randomly created. And that gives us this simple linear model. So you see, it's not a perfect model, but it does the job, right? So if we interpret this one, it tells us how can we get from this class to this class. So what we do is we explain the predictions by interpreting the local model. So locally, it's not perfect. Globally, it's horrible. So you see all of these points predicted as plus. So globally, it's a horrible model, but locally, it's okay, right? So locally, it's okay enough for us to use it and make interpretations. So this is LIME. So as we said, LIME is a very simple concept. What it does is it takes an instance of interest and it generates some random points all around it, weighs them by their closeness or their similarity or their proximity to the interest point, train a weighted interpretable model. In this case, it's, I don't know, it's a linear regression or some sort of decision tree model. And then, of course, explain the prediction by interpreting that local model. So it's a very simple algorithm, right? LIME is a very simple algorithm, a very simple technique. And it gets, since it's very simple, we can apply it to as many types of data as we want. So this, we have seen how to apply it for tabular data. Let's check out how can we apply it for text data. Just to confirm, does anybody have a question about the tabular data? It's quite simple, right? So it's a very basic algorithm, to be honest. And what you could, if you still don't like get all of these details down, just go to that book. It's less than 2 pages, and it will give you a very perfect example of this one. So LIME, as I said, is a very simple concept on its own, right? So it's very basic. And if you would like to understand how to apply it, for example, for what is it called? For texts or for images, then please just go and read that, and it's quite simple. Do you have any questions for now about this? Sounds good. So for text data, we're going to do a little bit of a change, right? And so what did we say? The first step, let me just take the steps and just post them somewhere. And then we do them together. So here are the steps. I'm going to send you the steps on Telegram. and you try to tell me how can we apply Lime for text data. So the first thing, select your interest, select your instance of interest. Simple. Here is the interest. Here's the instance of interest. It's a very simple spam detection model that tells you whether this email is a spam email. So looking at this, we have for Christmas song, visit my channel, wink. Right. So for Christmas song, visit my channel, wink. This is the instance of interest. Can you tell me what are the features? So we have to perturb the features, right? But before going there, what are the features for this input? Is it the characters?
It's words, either they
The
present or
tokens,
not.
right? Yep. So you could say words or the tokens. So for now, I'm just using tokens because it has this wink, and the wink is like very, very important. So exactly that. So instead of looking at the features as just characters, we look at them as words. How do you perturb the data set and make some random points, right? So perturbing the data set means you go to the feature and you change it.
We can keep some and choose different like samples out of this phrase. For
Exactly. So
example, for
instead of-
song, visit my channel.
Exactly.
Something like that.
Yep. So instead of saying for Christmas song, visit my channel, wink, you say for song, visit my channel. That's a different one. For Christmas, visit my channel. That's another one. So it's up to you, right? So you can just play around however you want. What you can do is represent this one as a one-hot encoded, sorry, represent this one as a one-hot encoded vector. This is exactly what you just said, but just a little bit different. Of one, not one hot encoded, sorry, just one. Yeah, imagine that my ones are correctly placed. So this pushes it here. Yep. So imagine that we are representing this input as just a number of ones, just multiple ones, right? Because we're trying to train a linear regression, and linear regression does not understand the word for, does not understand the word Christmas, but it does understand numbers. So what we're going to do is going to represent this as 1, 1, 1, 1, 1, 1, 1, and we're going to generate a new data set based on exactly what your friend has said by perturbing these numbers. So we can't represent the word 0.8 Christmas, but we can represent 0 Christmas means it doesn't exist, and 1 Christmas means it exists. So for example, in here, as your friend has said, for Christmas, we don't say it, song, visit, we don't say this, we don't say this, and then we just wink. And here the model gives us the probability. So the model gives us so we send this new, what is it called, sentence to the model, and it tells us the probability of being a scam is 0.17. And we have a weight that tells us the similarity between this vector and the 1, 1, 1, 1, 1, 1, 1, 1, 1 vector, which is 0.75. We have another one, which is there is no for, Christmas song, visit my, nothing here, wink. So Christmas song, visit my, wink. Also probably not a spam, and it has a closer weight or closer proximity because it just has more ones than this one. This one, for example, what does it say? For visit my channel, wink. For visit my channel, wink, the model has a very high probability that it is a spam, and we can see that it has the same weight. We have this one, which has just 1, 0. It has the highest weight because it's the most similar to the original input. And it says for song, visit my channel, wink. And we can see that it has a very high probability of being a sorry, of being a spam. So what we did is we simply took the instance of interest, represented it as once, as just a vector of once, and then tried to use that as perturbing the data set to get the different, points. We sent those different points into the model, the original black box model that only looks at text. So the original black box model only understands text, meaning when we get this 0, 1, 1, 1, 1, 1, 0, 1, we have to convert it back into a string of characters and then send it to the model. We send it to the model, we get our probability, we calculate the weight difference between this vector and the original 1, 1, 1, 1, 1, 1, 1 vector. And then using this, we train a simple linear model on exactly this ones and zeros, right? So linear models are very good when it comes to, numbers, but they're not good when it comes to text data. So this is why we have to make this conversion back and forth between text and numbers and Boolean representations of these text. So this is the only difference that is needed to apply basically LIME for textual data. And instead of getting this, instead of getting, an importance for feature, say, let's say the feature salary or feature number of kids, we get now an importance for feature word. So here we can see that the feature weights, the majority of them don't have that many feature weights, but here we can see that the feature weight channel is highly, highly influential in telling us that this email is a spam or not. Mainly, if he says that it's a YouTube channel or some sort of channel, probably it's a spam. But if Christmas, for example, nope, because your parents might talk to you about Christmas, right? So it's not something that you might expect to be 100% spam. Good also, it's not a very good indicator of a spam or not, but channel, it totally is. And of course, definitely this wink could also be a very big representation of spam. Now, before we go into how can we apply the LIME algorithm for images, we should speak first about this idea of superpixels. So the idea of superpixels is very similar or very much related to the idea of, what is it called? Selective search, right? So remember in the first RCNN architecture, we said that we will be using selective search to find potential regions of interest that could represent an object. So these regions should be similar in color, similar in intensities, similar in hue, similar in anything that you can calculate. And you just group those pixels together into a region. Superpixeling is a similar technique that does exactly that, and it just finds the interconnected pixels with similar colors. So it takes this image and it basically calculates the superpixels of this image, right? So why did we discover this? Why did we talk about this right before talking about LIME, right? Right before talking about LIME for images. Can somebody tell me why?
May I?
Yes?
I think that if we can group images using this technique, we then just consider, let me rephrase. In the LIME, we just consider local regions. And then if we have a technique for grouping, we just group and consider each group as a local and we work on it.
Exactly. So each one of these groups is a feature. So the goal is to understand, why did the model predict this as a horse, for example? And you would like to understand which regions inside the image were used or were most influential to make that predictions. So we will do exactly the same technique of this LIME for textual data, where we convert the words into features. Here we will convert different regions inside the image into features. The problem is we cannot do this directly on the image, like pixel by pixel, and just turn off one pixel and turn it on again, because that would give us a feature vector of like hundreds of thousands of features, and then you have to create a very large data set for that, and that would lead to a lot of work. But if we group them together into, let's say, 20 features, that is more reasonable, right? So if we group the image into 20 different regions and each region becomes a feature, that is more realistic. And that's exactly what we do. So we take the original image, we apply the superpixeling on it, and then what we do is we just perturb sometimes this region is off, sometimes this region is on, sometimes that region is off, sometimes this region is on, and we just continue building this data set, and we see whether the model classifies this image as a as a frog or not, and then whether it classifies this image as frog or not, or this one as a frog or not. And then we take that, train a local, as you can see, locally weighted regression on it. So we train a locally weighted regression on it, and that gives us, this is the region that is most important in our decision making by simply interpreting this locally weighted regression. And that could give us the following beautiful designs or beautiful explanations that go back to this first image that we have seen in here. So this is the results of Lime. So again, why do we use the superpixeling? Just to reduce the amount of features that we have to turn on and off to create that big data set that will be used to train the locally weighted regression that makes its decisions. Is it a little bit complicated how to use Lime for basically tabular data and for text data and for vision data?
I think I would have just a question about tabular data.
Yes.
Because as we can see, because for example, in the text and image, we have some kind of, we are using them at categorical, like we use the
Yes.
somehow hot encoding, but it's not necessarily the case for tabular data. But I believe we use some kind of like variance and to understand which ranges we should vary our values, right? Something
Yeah,
in this sense.
Yes. So it depends. For example, for you, if you're working with age, right? So if you're working with an age feature, it could range from, I don't know, 0 to 120. But if you're working with salary, it could go from 0 to 3 million, right? So they don't have all the same range. So this is why it's highly dependent on your data set. You define the ranges for each different feature.
So yeah, so it's like we use some kind, we define the certain statistical values to determine what is a local, right? The region we determine it using.
Yeah, of course. Yeah. So it's up to you, right? So this is definitely something that you just have to input with like metadata around your data. For example, if it's a categorical feature, then you just switch it on and off. If it's a numeric feature, then you will have to tell the model how to play with that feature.
Okay. Thank you.
Okay. And it's also for superpixeling, it's up to you to choose what is the superpixeling algorithm that you would like to use, right? I would rather not go into GradCam because it's also a very beautiful and very simple concept. But if I put it here, then I will have to put it in the exam, and I don't want you guys to suffer. So we will do it after the midterm. Okay. Do you have any questions about interpretability or about Lime or any of these different techniques? You have the lecture slides, the PDFs for all this, all the lectures. You have the videos, the Canva. So please do prepare well for this midterm. It's gonna be very easy, very basic. No cheating, please. And it's gonna be like, as I said, just couple of choices, and that's it. Nothing really major. So
Excuse me, would it be possible to how to say put group the lecture in one playlist in YouTube? Because it's it might be easily one can slip out of. I don't know. I'm not sure if I watched all of them. So that would be really helpful even for the future if they are just in one big playlist.
yes, I'm not very expert on YouTube, but I think it's easy to do. Let me try.
Okay. Thank you.
Any other questions, guys? All good? Then thank you guys so much for attending, and I wish you the best of luck for the midterm. And I will post today the project start thing where you just tell me the GitHub repo for the README idea of your project. And don't at all forget that you guys have a assignment, and the assignment is way more important than the midterm, right? So the midterm, it's almost super basic that you would always get like A without even like reading the lectures. But the assignment, it's gonna be more harsh in the grading. So please spend more of your time on the assignment. Spend like focus very much on the assignment, please. Okay.
One sec. The assignment out already, or I'm not sure. I'm a bit confused.
What do you mean?
Is it released on your
Yeah,
on Moodle?
You can't see it on Moodle. Wow, I didn't know. That's weird. You can't see the assignment on Moodle?
Yep, we cannot.
Can somebody show me your Moodle? Just like share the screen and show me Moodle from you. This is the applied machine learning course, right?
Ah, wait. Now, yeah, now I can.
Yeah, it's been there for like a week now. It's big also. It's not like small. It's like it's very big. Do you want me to put it like at the start? Let me maybe.
Yeah, no, that's fine.
Let me bring it up so that everybody can see it. Because it's very, very important, guys, huh? It's the most important thing. There you go. Now it should be the first thing you see on Moodle. Okay, all good?
Okay, interesting.
Yep.
Thank you.
Perfect. Good luck, guys. Have a great week. Bye-bye.
Thank you.